In the previous videos, we have mentioned about how do we construct the stress diagram in order for us to derive the equations for us to predict the stress in the prestressed concrete beam. It was also mentioned that we can adjust the P and also the E, which is represented by the tendon profile, as well as by the prestressing force, in order to generate resistance moment, counteracting the external load acting on the member. We know that the moment generated by the prestressing load will cancel out with the moment caused by the external load, which will lead to the remaining of the stress that is bounded by its stress limit. As long as the stress within the members are always within the limit, the prestressing member will be stable. This comes to the concept of the load balancing. The meaning of load balancing is we can manipulate the response of the structures under the prestressing load in order to counteract the external load acting on the member to keep the stress in the entire member here within the allowable limits of the stress. Taking this as an example, the simply supported beam is subjected to an UDL external load. To counteract the effects caused by the UDL load, a curvature tendon profile is provided and the tendon is pre-stressed. This will generate a series of counteracting forces, which the W and B, they can cancel out each other. In the case that the W and WP here is equal, the bending moment and the shear force caused by the UDL load is balanced by the prestressing load. The beam now is subjected only to the longitudinal prestressing force applied at the anchor. If the anchorage is located at the centroid of the beam sections, there will be uniform stress developed in the sections, which can be calculated by the prestressing load divided by the cross-sectional area of the sections. This case should theoretically cause the beam not undergoing any deflection. In the case that the UDL load is not equal to the opposing load caused by the prestressed tendon, then the bending moment caused by the unbalanced load, which is the difference between W and WP, must be calculated. Then you need to calculate the resultant stress distributions across the sections and check if the stress have exceeded the tension and the compression limits. These are some examples of equivalent loads caused by different setup of the tendon and their respective moment caused by the prestressing force. You may take this as a guide for you to choose appropriate arrangement of the tendon in the member for those which are subjected to various kinds of load. For example, this moment profile caused by the prestressing looks very identical to the bending moment diagram of a simply supported beam subjected to a point load at the midspan, except the moment is at the opposite directions. If you use this setup of the tendon profile to counteract the point load, the member should theoretically be subjected to only compressions. There will not be any bending stress caused by the external load. Alternately, we can look into this example. the moment generated from the prestressing force looks very identical to the beam subjected to an UDL load. Again, the directions of the moment is opposite. With that, this kind of setup may be applicable for the member which is subjected to only UDL load. Or you can look at this example. If the beam member is subjected to only bending moment, which gives a bending moment diagram of constant, this setup may be applicable. Similarly, for a continuous member, where there are fixed end moments generated as a result of the stress transfer, the effects of the UDL load can be best counteracted with this setup of the tendon. All these forces are generated differently due to different arrangements of the tendon. Because of the angle of the tendon, there will be componential forces in the horizontal and vertical directions. It can be simply estimated by using the sine cos theta. Based on the principle of static equilibrium, the horizontal components cancel out each other, and there will be resistance by the midspan of the member, which this and the vertical components at the supports cancel out each other. Similar concept is applicable for the other tendon profile. For the curvature tendon profile, the angle gradient of the tendons change gradually until to no gradient at the midspan. Such process of changing of the gradient will result a UDL equivalent load acting on the member. Similar concept applies here. In this case, the eccentricity is put above the neutral axis. This will generate an additional moment onto the member, which result it to have some moments at both ends. When the prestressing force is applied at an eccentricity, the combined effect of P multiplied the eccentricity will generate moments onto the members. By taking this as the basis of generating equivalent load inside the prestressing member, you have flexibility to choose various types of the tendon profile in counteracting the external load acting on the member. It is noted that you do not necessarily need to be totally eliminate the stresses in the member. It doesn't mean that this kind of tendon profile can only be applied for the point load, or it is not necessary for you to always use this to sustain the UDL. We have to go back to the fundamental. The concept of equivalent load is to generate the counteracting moment, which can reduce the effect of the uniformly distributed external load, so that the stress generated within the member are within the allowable stress limits, so that the member does not fail. There could be other factors that affecting your decisions of the tendon profile. For example, the methods of prestressing, whether it is pre-tension and post-tension, or some other unforeseen circumstances, such as the congestions of reinforcement bar, or the existence of the anchorage, or even the transverse hole within the beam section, as long as the stress are within the limits are acceptable.